Hello. So today, as you can see, I've already have one simulation up here. We are going to keep going through some other simulations. Um, and I've stopped this one just because since I do use the Falstad simulator, um, I thought I would stop at the one. This would be the circuit you would see if you first opened up the Falstad simulator and didn't do anything else. So what is this circuit? Those of you who may have experienced electronics before will know this circuit right away, and it's also classic circuit it's a classic problem, I should say, in other areas. So there is a inductor and a capacitor. Now, what is it? And then there's also this resistor. So what these do, so a capacitor will charge up and then it will slowly slow down the current as it charges. However, this inductor resists that change and eventually it will switch to the other side and it will go back this way, and the capacitor will discharge and then recharge here, slow down, and then go back and forth, back and forth. So that is an oscillator. However, since we have this resistor, that resistor burns up some of the energy, so then the oscillations become less and less. What it is called is a damped harmonic oscillator. And from what I said before is that sometimes, like if you have been familiar with any type of physics, you would know, or physics, or basically any physics, engineering problem, you would know that there's many variations of the damped harmonic oscillator. But this is just one, and it is the one that they choose to show right away. So yeah, I thought that would be the first one I would talk about today. Let's run it. You see what I mean? See, it's going back and forth, back and forth. But see how it's slowing? Now watch if I connect this. So now we've charged up this inductor, we've charged it. Yeah, we're running current through. And now, let's open the circuit. Oh, now the stuff is moving faster. The oscillations are more pronounced. But anyways, that was just one I thought I would show. Just because it is one that is there, and it always pops up when you first open up the Falstad simulator. Let's go. I took all the problems, all the circuits I'm going to look at today from Art of Electronics, that classic textbook I have been using. Last time I was looking at ones from different textbooks, but today I decided to look at this one. So I'm going to go to figure 1.33 on page 22 of Art of Electronics. Quickly go there. Figure 1.33 and RC charging circuit. Okay. So, and you can see, as I've been talking, I know this is a bit off topic, but you see the oscillations have went almost completely away. Now, anyways, let's go new blank circuit. And then we will draw inputs and sources, voltage source to terminal. So this is going to be our battery of sorts. And then draw, I think there is a switch somewhere here. Inputs and sources, clock, external data input, audio input. Didn't see that before. There's building blocks. Oh. Passive components. Wonder if there's a search on here. Add switch. There. So we got our switch there. I will draw resistor. There we go. Oops. I want two. I just want one resistor. Might as well make it longer here too. There we go. I'll draw what's passive components, add capacitor, add the capacitor in, and then might as well add a voltmeter. Outputs and labels, add voltmeter, because it asks us to add a voltmeter anyways. And I'm just going to connect all these via a wire. In the book, you'll see that they have them all at a ground, a common. So this is at 5 volts. So you see, we've charged it almost completely. Now, what happens if we open this? It's going to just maintain it. But here, how I think the better way to do it would be what's in sources? Passive components. Where'd that switch go? Add switch. So we are gonna add. Okay, I'm just gonna add a switch there for now. So you see now we discharge it. Sorry, I forgot. I didn't do what I usually do, describing what I think will happen. But, anyways. Oops. That's not the one I wanted to take. This one I want to take over. Sometimes I find that the Falstad simulator doesn't choose the one you want it to choose. That's okay. We'll get them all reconnected now. So this is just going to discharge until it gets to 0, basically. And now I'll open it up. So we're at that pico voltage. But now we'll close this, and when I close it, the current from the battery will flow through the resistor into the capacitor. And eventually the capacitor will get fully charged and will just be held right at that 5 volts. See? Charge, charge, charge. And now I'll open, close. You see now we discharge it through there. Now, a question now you might ask is, what happens if I say change this to, let's just go edit, let's go 10K. So, what I think will happen, let's see if I'm right, is that when I've changed that to 10K, now it is going to charge at a much slower rate than it was charging at before. So let's just close it. So yeah, you see, like at this point we were almost already at 3 or 4 volts. But now we're just getting to 3 volts. And because I talk so slowly, the 3 or 4 volts was like 5 minutes ago. But that is because if you go look at the textbook, the actual formula for the voltage, the charging, the time constant that people use, well, it's an exponential, so it isn't exactly linear. But the general rule is that in 5, what they define as time constants, which is RC, that's the time constant, is R and then C. Yeah, I think I can actually put a whatever. But yeah, you get what I'm saying. It's basically when you increase either the capacitance or the resistance, the length of time necessary. I'll just switch this around here. And the length of time necessary to charge or discharge will become more. So if we just stop this here, and I'll demonstrate it by now, we'll change the capacitance of, well, the value of the capacitor. by 10. Now let's go there. And you see how much slower? Like, it's a very, I guess this is very subjective. But it does make intuitive sense if you think of it. A capacitor charges, or a capacitor charges by having current flow into it. And it resists the change in voltage proportional to its capacitance. So given that, a resistor, the higher its resistance, the less current that will flow through it. So that means that the slower the capacitor will charge. The same with, I just realized I could probably make my screen bigger. There. Now I'll make myself a bit bigger here. So, get back to what I was talking about. So basically, if the capacitor has less current flowing in it, then it will charge slower. Now, since if we increase the capacitance, then that means that it's able to store more energy. So it will take more current, like more charge, to charge it up fully. Another good place to go learn some more about this type of stuff is actually the Hyperphysics website. I'll just go it before I move on to the next circuit. I've spent a lot of time on this circuit actually. See this one, Hyperphysics. It's a really good. I love it. I don't know what university maintains it, but it's a great website. Oh, my dog has just broke one of its toys again. But anyways, let's go to the next one, which is 1.38 on page 24. Which is an RC timing circuit. Uses a comparator. You can draw two active building blocks. Yeah, I might as well use this one. I do have compared to two. I've thought of trying to do a live stream where I build circuits, since I like doing that a lot too. I like doing that even more than this, actually. This works the way that I would think it. I want a push switch. Okay, yeah, good. That works the way I would think it would. The thing is, I haven't really figured out a good way that I could do that in a live stream, like building circuits in the live stream, because I think I'd have to do part of it on my phone, and yeah, I just basically don't know how I could accomplish having part of it on my phone while the other part on in the computer screen, that you could see the output of my Analog Discovery 3. If any of you know good software which I could, or like a method where I could simply just link the two up, that would be great. Just realized, since we're dealing with perfect things, I actually don't have to do what I was going to do there. So we'll just keep on going here. Off topic, but since I'm just assembling this circuit, and you might get bored as I'm talking. You might get bored if I talk about this anyways. But I have been listening to a great podcast. They just covered Richard Nixon. It's a podcast about the 1960s in the States, which I had no idea how wacky of a year that was. Like, that was the year Martin Luther King got shot, Bob Kennedy got shot. It was just insane. Well, let's go down here. And we'll go edit this. This is going to be a 620k resistor. Quite a big resistance. Yeah, I'm just going to hit this one so that I can have a chance to guess what's going to happen. Oops. I have to go 360k. I don't know what I did there. I have num locks on. It's odd. So, 360k for that one. Yeah. I'll draw. Wants one there. And I think it wants one over there. One there. Passive components. We want a polarized capacitor. You want it that way. This can already center this a bit. I did that by zooming in, then zooming out. Might not be the best way to do that, but whatever. I do things differently sometimes. Let's go add ground. Add ground there. So add ground here. And then we're gonna add another resistor. It's sort of gonna be in the way there. Sorry, this is a bit messy, but just put it as 6.2 meg ohms. I put it as. Okay. Draw. Now just go and put sources. And then I think there's one where I can just select a test point. No, outputs and labels. That's where the test point is here. Add test point. I want one there. And I'm going to right click, view in new scope. So now I can see the test point in the new scope here. But let's first, I need to do one more thing. Need to put a ground here. Just that. So now before, and I also need to add the 5 volts. Add voltage source right there, 5 volts. Okay, now I can talk about it. First of all, let's see. Wow. Doesn't really have a I'll see what it does. But anyways, when I flick this switch and it's running, so basically at this point, right here at the negative voltage, which should always, in theory, be lower. Well, not always, but from the point of view of the comparator, that this input should be the same as this input or lower. And when it isn't, then it's going to output 5 volts because it thinks it will help it. So this point, this negative input, will be always, like, say, this is about 1/2 of this. So that means 2 times the voltage will be burnt up there. So I'm just going to give a good estimate. let's just do this and try to do this in my head here. So if this was divided into thirds, if we had, then that would be 1, and then 1.67. So I would say that there'd be about 3.2 volts here or so. But when we flick this, well, then this capacitor is going to slowly charge up to the full 5 volts. And then this will output 5 volts for the time that it takes this capacitor. Yeah, I wanted 10 microfarads there. So this capacitor, when it charges up to that 5 volts, then it's going to discharge itself through this mega ohm resistor, and eventually it will go below the voltage at this point. Let's just run it. So you see right now nothing's happening. It's 1.8 volts, so I was wrong there. Oh yeah. Yeah, no, I was right, but I always get that mixed up. Because yeah, so this will burn up 3.2 volts. That means that there's only 1.8 volts left. So my logic was right, but my math or understanding was wrong. But now when I flick this, that means that this capacitor, if I'm right, this capacitor will charge to 5 volts fairly quickly, because this is only a 1K resistor. And then when that happens, this is going to go higher than this, which will make signal to this to output high. And then this will slowly discharge through this 6.2 mega ohm resistor, which when it does discharge below 1.8 volts, then this will go low again. So let's see if that happens. It doesn't. Think here what we're gonna do instead, we're just gonna draw a op amp, an ideal op amp. So I think it's gonna give us a better result. We're gonna edit this. So still doesn't give us the right result. Oh, it's just taking a while to discharge. Let's reset. So yeah, now it has given us the right result. How long did it say this would be? Oh, it's 1 minute. We don't want to wait 1 minute. Well, you know what we could do? We can up the simulation speed. There, yeah, that's what we'll do. We will up the simulation speed. So now we're simulating much faster. See? Go there. Actually, yeah, we still won't get what we want there. So let's just go here, edit. We'll just put K. Well, now let's do 100. Okay. We'll just see what happens then. Now we're going to click this, and then it should, again, charge this capacitor quickly, and then it should be near 5 volts, which will put this to go out to 5 volts, which we've now just defined as a regular ideal op amp, and set its rails at 5 volts and 0. And then once this is at 5 volts, So this is output in 5 volts because it has this is the non-inverted input. So we will try to up it to try and make this correct, even though that there is no feedback in this case. Yeah. So and then once it does that, this will discharge slowly through the 100K. Eventually get into the point where we'll just output what it is close to 0. Let's see if that's what happens. Click this. So yeah, we're outputting 5 volts, 5 volts. And then we're watching this. See, it's going down, it's going down. It's at 2.2. And there. Now we're back. That is it away. Yeah. So anyways, that is that circuit. Sorry it took me a fair while to get its understanding of it. As you may know, it's still falling down there. Eventually it should stop, because it has a minimum output of 0, so unless this might just be a weird bug in the system of the Falstad simulator. Not sure, but it could be. But I think we should move on to the next one. So that was 1.38 on page 24 of Art of Electronics. So now let's go to 1.92 on page 43 of Art of Electronics. Here, I'll just put this again so that we have something to look at. Oh, look. So nice. I could actually add even more scopes if you wanted. But yeah, if anybody wanted to hear some, or like a view, if they had an idea of a circuit for me to look at, I'm always interested to see or try out a new circuit. But this now, we're just going to do a simple high-pass filter, which I guess that gives away some of what I'm going to be doing here. So we'll go there, and then go capacitor, there. Oh, I did that wrong. This is a low pass filter that I did. I want to do a high pass filter. We'll draw in the test point. Test point right there. And now we need to draw in the ground. The other thing, though, I have thought about it too, for doing, is a video on each of my things that I have bought at any one time through DigiKeep. For some of the weird components I just have sitting around my shop. What was I going to add? Because, yeah, I do have quite a bit, and some of it doesn't make that much sense why I have it. Let's go add AC voltage source, one terminal. I'm just doing this to be easy. Here, I'll stop it. So I didn't really pick these all that well. In the book, it doesn't have any that they actually pick and say, oh, this is the one we're doing. It just has whichever one, like just blank values, and this is what a high pass filter looks like. So, but let's just think of what this circuit is doing. So, when we know that capacitors resist changes in voltages, so if you have a very slow change in voltage, then yeah. So if you have a very slow change in voltage, you can imagine that this eventually, this capacitor, if it's slow enough, this capacitor will just charge fully. So then you won't actually get the signal because it will be fully charged. Whereas, what is that? Yeah, that must be how it works. Let me just think for a second here. Yeah. So yeah, because at DC current, this looks like an open circuit. And then at AC current, this looks like a short circuit. Yeah, that's what it is. Okay. So let's just edit this down to 0.1 hertz. Apply. Okay. Run. So you see, we're driving this though. You see, it is changing. You might say, and it is. But we are driving it. Actually, let's just go to 1 hertz so that we can actually tell. So let's wait till it gets. Oh yeah, now it's starting to fall already, and it only got to 260 millivolts. Now let's see what it gets to on the other side here. And you'll see what I'm going to get to my point here soon. I'm sorry if it sounds somewhat incoherent. I'm sometimes incoherent, but that's okay. In the meantime, if anybody did have any interest in hearing about any other circuits, please say so in the comments. So now we're reaching the max that it was in the negatives. We'll see if it gets, yeah, it's going to go a little bit higher, it looks like. And yeah, now we're starting to fall. So only 313 millivolts. So 0.3 volts, say. Now this, you see its max voltage was 5 volts. So, okay. So that means we should be seeing here, and I'll put this in the view and new scope. So let's edit this now to be 1K hertz. We'll slow down the simulation speed. So you see, though, we're getting to 5 volts. Let's edit this to horizontal scale. I want to go. Okay. So you see, now we can see the thing there. It's going, I want to see the voltage. It's going from minus 5 volts to basically plus 5 volts. So when we up the frequency to 1 kilohertz from 1 hertz, at 1 hertz we were basically seeing none of the signal get through. It was only 0.3 of a volt of the full 5 volts. When we upped the frequency to 1 kilohertz, then we got basically the whole 5 volts through. Now we can see there is something called an F3B point or 3dB point, where it's the output or the signal will have been attenuated by roughly 70%. And it is calculated by calculating 1 over 2 pi RC. Now, I will try to I'll try to estimate it on the fly here without using my calculator, which is what I like to do in this, just because I'm trying to get a more intuitive grasp of circuits by doing these live streams. So we have a 10 microfarad and 1 kilo ohm resistor. So, and the frequency we're looking for is 1 over 2 pi RC. So let's just estimate the RC part of it. So we can go to that to 10 millifarads, which would be the same as multiplying by 100, I guess. So, and then we have that divided by 2 pi. So that would be what, 6 divided by, or 100 divided by 6, so say 5. I would say around 20 or 30 hertz is what we would be looking for that point. So let's just put this down to 20 hertz. Go okay. Now I'm looking to see if, I guess we can up the simulation speed a little bit now. If it goes up to about 3 volts. So we're getting to 2 volts, 2.4 volts. Oh, we might get close here. Might actually get it. And I'm looking for 3 volts again for those of you who are just tuning in. Ah, not quite. Okay, let's edit this. We'll put it to 25. Now I might want to increase the simulation speed here just so that we can actually see it happen eventually. There. I've increased the simulation speed again. See, it's moving faster. And it's decreased the simulation speed here. Okay, so now we are, and yes! Oh, might be a little bit too high though. Yeah, it's definitely too high. That's too high of a voltage that we're looking for. So let's turn it down to, say, 22 hertz. Okay. Now we'll up the simulation speed again. Down it. Now we'll just watch for it to hopefully get to about 3 volts again is our goal. And then I shall move on to the next circuit that we're excited about. Oh, I've missed it. It's a bit high again. Bet it's going to stop right at that 4 volts. Nope, a little bit short of it. I'm going to move on anyways. I think we understand what this circuit does. So let's go to page 77 of Art of Electronics. Figure 2.10b. Oop, I've flipped too far. So now, yeah, still one too far. B is what I want to do. Okay. It's just a pulse, and then looks like some sort of push-pull type thing. Switching the high side of the load, return to ground. Well, let's construct it. I'll delete all this. We're into the transistor chapter here, so now we'll be talking about transistors, which I'm sure everybody just loves and adores, like they do all their circuits. Add resistor, then Q2, which I guess will be Q1 here because I'm gonna draw it now. It's an NPN transistor. Then the next one will be a PNP transistor, but first we will draw in the other resistor. So you get a resistor here. Oh, oops. I want to just move everything. Then it wanted to drag everything around again. I'm going to drag everything down again. Right there. And I'll draw that resistor there. That's going to be our 15-volt rail up there. But first, we'll draw the PNP transistor. Right there. Oh, oops. Oh, I don't want to see that either. Yeah, so that's good. Now we will add a wire. Step to there. Draw inputs and sources. Voltage source on terminal. There. Oh, I better stop this. There. Add wire. There. Now. We will connect that to ground. Actually, might as well add a resistor and how about let's say a LED. This for shits and gigs. Right there. Now, I think we can draw in a pulse. So let's see if we can do that. Inputs and sources. Voltage source, clock, AC variable voltage. External voltage. Let's just add a square wave source. Then I will edit it to be like 0.001 hertz. Cancel. No. What we will do, here. Cancel. What I'll do, delete, is reset this. I will draw in a switch. Along with a voltage source. Then that will be our pulse. I'll just click it and it will be a pulse. You know? Inputs and sources. Add voltage source, one terminal. Right there. Now we want that to be 3. Edit. 3. Apply. Okay. Edit. And we want this to be 15. Apply. Okay. So, now, I will try to explain what I think will happen while I do this, like when I run the simulation. So, what I think will happen is that when I turn, well, actually, I should get all these resistors right too first. Sorry. 3.3. apply, okay. Oops, it's 3.3K. That won't work very well there. Okay. And then, yeah, this is fine here. And this is 10K. Okay. So basically, if you think of currents, which it's usually best to do when you are dealing with transistors, when I'll open this switch, when we apply this, like this 3 volts to this switch or this transistor, then there will be current flowing into its base, which, given that it has a beta roughly of 100, it will draw. So we have 3 volts. 3 divided by 10 is 0.3. So 0.3 milliamps, 0.3 milliamps going through. It will be trying to draw about 30 30 milliamps max through it. Now given we have 4.3 kiloohms there, 15 volts. These that is bad choices for math, for in the head math. Let's just say it's 4, and that's 16 there. Then that means 16 divided by 4 is 4. And so about 4 milliamps, just under 4 milliamps max would flow through there. So it's not going to be flowing the full, but there will be about that much. And then I see what will happen. Since this will be calling for extra, then it will activate this PNP transistor as well, because some current will flow through its base to try and satisfy this, which then will require the rest. So like, since only 1K is here, that means the rest of this 3.3K is there, and that means that this will be burning up. I am guessing, if we check this voltage right here, it is going to be, so 15 volts. Let's just say this is 3K, because I want to do in the head math. So, well, then we have 4 parts. So again, let's say that this is 16 volts here. I know it isn't. I'm just trying to do it in my head here. It's easier this way. So that means that 4 volts would be burnt across here. And then 12 volts across here. So that means that it would be 12 volts seen here. It means, say, about a volt there. So then would have 11 volts here. Say it's 10. It's, again, easy math. That means we have 10 milliamps flowing through here. So say I'm guessing about 10 volts here, and then that would be about 10 milliamps flowing through. So let's run it. So right now we have nothing, which makes sense, because there would be, like, yeah, there's just a full 15 volts there, 15 volts there, and there's no current flowing through anywhere. So let's turn this on. And now, let's see, we have almost 14 volts there. So I was wrong. It actually, there must be less current flowing through here. No, it's still about 4 milliamps. But it's it is mostly coming from here. Anyways, let's check the voltage there. So that is almost 15 volts there. And then most of it flows through there. So I did misunderstand something in this circuit. Let's maybe just think about it as we're watching it simulate here. So what did I misunderstand? I did get how everything would get activated, because you see when I unclick that, it stopped. So I got that. that this was activated by this wanting current from it. Because this wants about 30 milliamps of current. Like max it would ask for. And wasn't getting it. It still doesn't get it. But in this case, it was only getting like a microamp through it. So I think what I was misunderstanding, and I've done this before, is that since this is being held at 15 volts, this only has a one diode drop right between them. And that means that this would be held at about 14.4 volts. And then this collector here, well, it would be tied almost directly to the emitter because the current flows from there to there. So then it would be close to 15 volts as well, or 14.4. Let's see. Yeah, that says 14.4 volts, which makes sense then. And then that is why this only draws under a milliamp, because it's actually not dropping that much voltage. Like you see, it's only dropping 673 millivolts. Now down here, we are at 14.9 volts. That would be because of how the PNP transmits current, that it just basically shorts these two here, I think. Yeah. So sorry about that. I did misunderstand that circuit for a second, which happens when I'm doing things on the fly. So that was page 77. I think we should move on. Probably have time for only one more circuit. If anybody has some more ideas, like if they have a request, they can put that in the chat. Yeah. I'm just seeing, I'm looking at the YouTube studio mode is how I can see the chat on here. Yeah, so I'm just going to check mark that off. And we will go to page 101 and do figure 2.58. Sorry. I don't like having any dead silence. As you can see, I do like to talk, in fact. I don't know if you've picked up on that, but I do actually like to talk. Maybe that's one of the reasons why I'm doing these live streams too, not just for my own learning, or my own, I guess not so learning, but intuition creation. Anyways, we'll go, so yeah, we did a new blank circuit. We're going to do figure 2.58 on page 101 of Art of Electronics, which is a PNP current mirror. Like a, yeah, current mirror made out of PNP transistors. So connect that. Connect that. Oh, oops. Messed up again. Right there. Okay. Now. We'll add a wire right about. Try to get about above them. We'll stop this too before we started. Then we will add a resistor here. Oops, frick. For frick's sakes. Then we will draw, add wire. Add ground. There we go. Now, yeah, I think this one is just, nope, that has a load. So we'll draw in our classic load of, now I wanted to do two. Okay, but anyways, we're going to draw in our classic load of a couple resistors or a resistor and an LED. So that is just always a great load, mostly because you also have a beautiful, beautiful, beautiful shining light, of which is the LED. So now, let's do here. Then we'll add. No. This one. And they did plus 15 volts. Of course they did. They always like doing high voltages, which I couldn't do with my Analog Discovery 3 when I first got it. There we go. Okay. So, wow, they set this at 14.4K. That seems like a very, very odd thing to set it at. There we go. So basically, how I think this will go is that left side PNP transistor will get 15 volts minus. Oh, okay. No, I see why they did 14.4K. That makes the our favorite current, which is 1 milliamp. And then that 1 milliamp is going to get drawn out of both of these bases. Right there. Both of these bases here. Actually, look, wait, yeah. No, wrong. I always do that wrong. Okay, I am going to draw in an ammeter here, just because, you know, then you can see it better when we go to look at it. So, about 1 milliamp should be going through here, which will trigger that same coming through here, but it will be roughly 10 times that. So we should see, or 100 times that, I mean, should see about 100 milliamps. But that can't be right. We'll only see about a milliamp coming through here. Yeah, no, that's right. Yeah, sorry. I was thinking weird again. I think we'll only see a milliamp coming through here. We will see milliamp through here. Yeah. So let's see what happens. And yeah, we see some microamps going through there. But we do see exactly a milliamp coming through here, because that is at 14.4 volts. So most of the current would be going from that emitter to collector voltage. So I was slightly wrong in that. I thought it'd be coming through here, but that was wrong. And then on this side, we should have about a milliamp again. And we have not quite a milliamp. We have 980 microamps, which is somewhat close. Like that's 20 microamps away. If you're dealing in some cases, that might be important, but most of the time it isn't. So no, it's basically a milliamp. We'll round up in this case. Yeah, so 854 it is now. Done that. Yeah, and then it said something about the early effect here, which I was thinking of doing that one too. But I think since we're lacking some time, I might just move on to page 253 of Art of Electronics and do figure 4.56, which then we'll get back into op amps. I guess I could demonstrate just for those of you who may not get what we're looking at here. I'm going to change this to 5K. So now since this is 14.4 volts, we'll just round up to 15 volts. Then I should see 3 milliamps, just under 3 milliamps, like 2.9 milliamps, going through here. And then it should also be going through this LED here. So I'll apply it, click OK. So we see 2.86 milliamps. My estimate was 2.9, so I'm pretty close. And then over here, we see 2.8 milliamps. So again, fairly close. So let's go File, New Blank Circuit. Now, I'll check that one off. Ooh. Meter calibration. See if the next one I picked was a bit easier. That one seems pretty hard. It's a millivolt thing. Oh, a peak detector. Okay. Let's see if we can quickly do this one. So now we need to add active building blocks. Do the plus on top. And again, like I guess let me know in the comments if you think that watching this type of format, but like live here, but instead of using the simulator, if do it like if making what am I trying to say? If constructing the circuits and analyzing them in real time, like actually constructing the circuits on the bench and then showing you the output in the Analog Discovery 3 would be something you would want to see. I don't know how I would accomplish that right now, but I think it would be cool. The main reason is because like a lot of the times I will go and I'll construct something in the Analog Discovery 3 and I can you should, while I'm constructing it, I would assume that you would want to see me constructing it, and I'd have to tie in my phone for that, and then I'd have to overlay it. Like I'd have, instead of seeing my face, I think I would have you see that thing. So I could try to balance my that video camera on it. But yeah, let me know if any of you think that would be a cool thing to see, like live constructing of circuits and simulate, or not simulating them, they'd actually be being done, that we'd be analyzing them, I guess, or like reading data from them. So I think it'd be fun, and that's how I like to learn about circuits more anyways. It's just this, I honestly did this just as a test to see, because I was actually soldering live one day, and people tuned in, and I was quite surprised because I was just soldering things, so I didn't really think that it was that interesting of a thing to tune into. So I decided to try and make something a bit more interesting. Yeah, and I think that constructing circuits might be even more interesting than that. So, if you wanted, please let me know if that's something that you think would be fun or entertaining or whatever you are looking for on this great and wonderful YouTube. But anyways, I'm done connecting this circuit up. I just need to, well, I guess I could put it in the input and sources. So we'll add the voltage source. Let's start at 2 volts. Okay. So what will happen when I turn this on? We're going to see 2 volts at the inverted input. So that means that this will want to move itself up. We'll go up to try and correct it, because this non-inverted input wants to be at 2 volts with the the inverted input, the negative input, wants to be at 2 volts with the non-inverted input, the positive input there. So it's the output is going to go up to 2 volts, basically, because what's going to happen is that this, since we have feedback incorporated in here, if we didn't have feedback, you'd basically see that go way up to 15 volts and not be able to do anything. But since we have negative feedback in here, that means that this is going to rise up to 2 volts, and then it's going to stop rising. It's just going to stop. And then if we took this away, well, actually, this won't change in voltage. Like, it's not going to backflow or anything, because we have this diode here and this capacitor here holding the output there. So what it does effectively is then, like, when this rises up to 2 volts, then this will also go to 2 volts and it will stay there. So, yeah, does that make sense? If I go, like, say this is at 2 volts and then I drop it to 1 volt. Well, now that I've dropped it to 1 volt, this guy is going to want to try and go rise it up. So it will try and push it higher. But since this will be holding it above it, this won't actually change any voltage on this point here. I don't think I explained that totally correct. Well, let's see if the simulation will help you at all. That's weird. That rails at 4 volts. So now if we added it, we go to 5 volts. Apply, okay. So went 1 volt above the 5 volts. But it held it at 6 volts. I think it must be that there isn't a fast enough change. But let's go here, apply. And you see, it's still holding it at 6 volts. And the reason for that, see here, it's driving minus 15 volts there. But since this diode is in place, the diode prevents any current flow from that. So make sure that the voltage does not change at this point. My dog is just trying to get some more attention from me. Yeah. So let's change this to 8 volts. Apply. You see now it's jumped up to 10 volts. I think that jump is to do with the simulation software. But anyways, we are at 9:05 now, it is. And I think I've demonstrated this circuit enough. Again, if any of you are still listening or are interested, again, if you want to hear or see me do a live stream where I don't just simulate circuits, like construct and simulate the circuits in the Falstad simulator, but instead I go and I look at these circuits and I take real components, assemble them on a breadboard, and then use either my multimeter or the Analog Discovery 3 to show you what is happening. Let me know, and I will try to do that as a live stream. But anyways, thank you all for tuning in, and I hope you tune in next Friday at around 8, where I will do this again, or I might try to construct circuits on the breadboard and evaluate them live with you.